going to begin hypothesis testing. Lots to say about this, but I don't want it. So it's kind of how I feel. But there's a balance in here. We'll talk about it in a second. Is to where we can make this maybe useful and not quite as controversial. But understanding the issues is the goal. So in academia, knowing things, how to do problems, solving problems, getting A's on midterms is not the goal. It's understanding and being able to convey it. And being able to apply it. It's also useful. But understanding is our primary goal. On that note, I'll say a few things about the midterm. There were questions that were designed to gauge your understanding. And I can tell. And you can tell if you understood it or not. And you can kind of tell, like, where were the gaps. I'll just say a few comments. These are critical errors. Critical errors. And I see these every year. So it's not a statement about this class per se, and people that make these errors on midterms and don't make them on finals usually are pretty satisfied with the way it all works out. Again, that's the goal. I will say something about these critical errors that I see every single year. I saw more of them this year than I've ever seen before. So maybe that makes some of you feel better. Okay, good. There's other people. I usually see it once or twice. I usually say a whole bunch throughout the semester trying to get you not to make these mistakes, but just because I say something, it doesn't always turn out the way that I hope. So, there's some of these critical errors. I counted 8 of one of these critical errors, where I was just like flabbergasted by it. And I think there's a reason. So there's always a reason, right? So it's like, I think it's maybe over the last 2 years, some of the classes that people were taking online and they're just getting slammed with lots of work at home, turning it in a pile of stuff, not really getting any feedback. And so these errors can continue. And I think, and then you take advanced classes and they keep showing up and they cripple you. Working through these, there's always time. So as long as you digest. And what I've found in my own experience is when I make mistakes, I learn best. So, now I know what not to do. And even when I know not to do something, it's like, oftentimes I think, well, I want to try it anyway. I want to just see how, like, what happens. And so just to get that experience, because it's so valuable. And so if you get something out of this, I guess that's okay. So it's all a matter of perspective. Divided by matrices. I joke about this, but then I don't joke. And so, this is 8 times that I saw it in this class. Division by matrices. There is also weird factorization with matrices. So, weird rules in linear algebra that if you tried this, you'd realize that can't be the answer. So again, some of this is nerves that happen and people just write stuff down, and I'm sure I've written stuff down where it's like, I don't even believe that. I don't even know why I wrote that down. I just was in a rush. So it could be some of that in some of the factorizations. But where I kind of saw this was in this problem, where we were coming up with a likelihood for beta given x and y. And the correct way to do this in terms of beta is to write down whatever the distribution was. So this would look like this. 1/2 y minus x beta. Sigma inverse y minus x beta. And we want to think about this in terms of beta. And so this is the same problem that we've seen before. It just had to do, there's a dense sigma in here. The sigma things don't cancel. And so I saw weird stuff where this would get factorized out in funny ways, and I saw weird stuff where you'd start dividing by matrices for some reason in the middle of the problem. It doesn't bother me as much when the 1/2 gets like thrown around in weird ways or something like that. I did see that in that distribution problem. The half not getting carried right. It's too bad because we've played with that problem so many times now. think that it would be automatic. But if it's not, there's time to correct this. And I'll find out if you know how to do it eventually. We're going to use it on the next homework. Anyway, this thing right here is just e to the minus 1/2. And I'll just factorize it, or just write it out. So y transpose sigma y. So I'm just expanding. There's two cross terms, and I prefer to write them like this. Minus 2 beta transpose x transpose. So I'm just flipping this thing around when I transpose it. So when I transpose over the top, it flips everything around. If you don't believe me, check the dimensionality. And just work out the multiplication and the addition that you're implying. And that's all linear algebra is. So after a while, you start to see the rules. It's automatic to you. Minus 2 beta x transpose, that thing is there. Some people had some magic with this, and they just pulled it all over the place. And so times what? There's another term, so one of those shows up like that, and the other one shows up as the transpose of that. They're scalars, so they're the same thing, so they add together, and that's where you get the minus 2 from. That's where I picked it up. So plus beta transpose, x transpose, sigma inverse, x transpose, beta is the last term. And so that's how you do linear algebra. Everything carried through. If you think you're doing something weird in linear algebra, you'll know it. You'll feel it. Let me just ask the question, what's the dimensionality of P in this problem? So I haven't stated in terms of this, but I think on that midterm it was P, and a lot of people thought it was K. I marked you off like a half point if you made that mistake. But if you drug this matrix around in funny ways or divided by it, you probably get a pretty big thing. And so I will offer you the opportunity to go correct those mistakes so that you can write them down. Writing down is usually helpful for learning, and turning them back to me and letting me know you know where your errors are. So I'll give you that opportunity. We'll fix up your grade. So anyway, it's like this. So this term doesn't matter. If I ended up taking the posterior of beta given x and y is still proportional to this thing because I multiply by my prior one. I gave you that flat prior. If I gave you the conjugate prior, there would be a little bit more math to do, but it would be the same thing in spirit. So where do I search for the quadratic term? The quadratic term. I look at whatever's multiplying it. In this case, it's multiplying it in matrix fashion. So if these were scalars, you could see that what the quadratic term looks like. It looks squared, but in matrix format, it looks like this. And so this is the variance inverse. So this is the variance of beta given everything else inverted. So I just take that thing and I invert it. I don't divide by it, I invert it. And we know what that means. It means that I find the matrix, that if I multiply by that thing, it gives me back the identity. So that's what that looks like. And then where do I go for the expectation? I look right here by the minus 2 linear terms. So I take this thing and I multiply it by the inverse of that. So variance, I'll just write it down, x transpose sigma inverse x transpose. Inverse x, oops, there's 2 x transposes right here, right? Let's just get rid of those. So dimensionality doesn't match. I'd probably catch that, you know, if I wasn't standing so close to the pool. So that's the variance. So I take that thing and I multiply it into this. So that's going to be the expectation for beta given everything else is equal to x transpose sigma inverse x transpose sigma inverse y. This is the generalized least squares solution. So maybe you've seen it in a regression class. You should have seen it on the last homework when you were playing around with that little gamma parameter and integrating it out. The solution to beta had this form where sigma turned out to be a diagonal matrix of all those little gammas. And so is what you were working on. We can go over that in a review session, but you have been introduced to this concept. It should have appeared. So what I like about math and stats and computer science classes, computer science maybe not because I can't find my errors that quickly, you know, and they kind of drive me crazy. Back in the day, you just need to spend a lot of time. is you know at the end of it if this is the correct solution. You can always verify. So there should be something that you plug back into and make sure everything is right. Anyway, these solutions probably make some sense to you. It's awfully similar to that. But the sigmas don't pop out in Factorize in this one. And so they don't come out here and come out here or anything like that. You don't divide and then re-throw it in there. Anyway, I'll not say too much more about that, but that's how you do this problem. A lot of you got it right. I ended up asking for a problem like stuff like this. Expectation of x tilde given everything else. And I saw some funny answers for this. So I'll just say, here's how you do the problem. So x tilde given p. And I'm just gonna, turns out I don't need to know that because everything is conditionally independent given p. So given x, right here. So I had weird answers. I had answers where this was equal to p. This is not equal to p. There's no p in this equation. So I had answers where this depended on x tilde. So I had function of x tilde. So it can't be. X tilde is the random variable. What does that mean? So this is the thing that we're integrating over. And so if it has x tilde in it, what are you plugging in? How are you even thinking about this? It's a distribution over x tilde. There's no number to plug in there. So it kind of tells me that the probability theory is off. Like, what are we even doing with these equations? Expectations are always a function of this. This will have your alpha and beta term in there. So, but ultimately, this is just, this thing is a Bernoulli right here, so this is the expectation of p given x. And we probably know what that is. So it's going to be, this is going to be some beta. I'm going to say that beta has parameters alpha tilde and beta tilde, so it's alpha tilde over alpha tilde plus beta tilde. It's going to be that thing. So it's the same expectation as you get for the expectation of p given x. So that's kind of nice. There was a little bit of a trick. I didn't mark people off too hard here. Variance of x tilde. Do the same thing right here. Some of you actually knew what some of this stuff was. I was pretty impressed if you knew the variance formula for a beta. You didn't actually need it in this problem. Variance of x tilde. P given x is equal to the variance of the expectation of x tilde given x in P.
And that's supposed to be a plus?
Yes, please?
Plus instead of equals?
Oh, plus, yeah. Yeah, add those two things together. They're not equal. So, we'll just kind of chisel away at this for a second. This is the expectation, the variance of x tilde. I'm not too sympathetic if you didn't know what it was, because you can work it out in like a minute if you've gone through your probability class recently quick. So it's like the variance, if you know how to decompose variance into, I'll just write it down like this, variance of something, I'll write it down as z, is equal to the expectation of z squared minus expectation of z all squared. You should know that and use that regularly. It makes your life easy. We did this for Bernoulli pretty quick. I would encourage you to do it in p times 1 minus. So given all this stuff, this is the expectation of p minus p squared given x right here. So this is a linear function, so I can break that into two terms. And the expectation of p squared has something to do with variance. And it turns out what's beautiful in this whole thing is the variances end up canceling in this equation. So there's this minus thing. So expectation, I'll just write this down, p squared given x is equal to the variance of P given X plus, let's swing this over, the expectation of P squared given X. I didn't mark you off too hard. If you weren't able to carry this through, if you got up there, you missed up to this point, you just missed a couple points. So you have this thing right here. It's going to slide in for this negative term. There's going to be a negative there in the variance. You didn't even need to know what it is. But I think what I really want to say is this is definitely not a function of x tilde. So there's no x tildes in there. That one bothers. So I'm not going to lose any sleep over it, but if we can fix the problem, I would appreciate it. There were also some things where it's like parameters didn't appear right in these sort of equations. But I would say these are the two like overarching, problems that I would see, the ones that bother me the most. Let's just do real quickly the t distribution problem, because there are a lot of problems with that, and I thought we had done this problem so many times, and I would be willing to show you how to do it in review session. Some people ask me after class. And so not knowing how to do it at this point, it's like, yuck. But let's learn how to do it. The matrix format one was a little bit harder than you just did on the homework, if you could do that one, which a lot of you weren't able. You should be able to do the scalar version pretty easily. But let's just write down what we are going for. So we're going down for some distribution f x given mu and sigma squared. And I'm going to write this down as an integral of f x given mu sigma squared over gamma right here, where I've got some distribution on gamma. This is going to have a couple parameters in here, alpha and beta, and the question concerned alpha and beta. I'm going to integrate over gamma from 0 to infinity. Right here, this was a gamma, alpha and beta. This is a normal with mean mu, invariant sigma squared over gamma. This right here is not a function of gamma. That's that second biggest error that I see people make where I'm like freaking out because it's gotten integrated away. It's not in the equation. It shouldn't be there. Some people left it in there, weren't sure what to do with it. Some people handle kind of the manipulation of everything a little bit strangely. Let's just do the problem and learn how to do it. You'll use it on the next upcoming homework. I'll probably still give you another day before I post it. So what is this going to look like? This is going to be 1 over root sigma squared over gamma. I've got rid of my 2 pi in all of that. E to the minus 1/2 x minus mu over sigma squared divided by gamma. I'll deal with that in a second. I'm going to throw it up.
X minus mu squared.
Thank you. So normal distribution. A lot of people took products over this and started throwing a lot of xi's in there, and I couldn't understand even what was the point of it. So it doesn't even ask for a question like that. There's no xi's introduced. So kind of strange. It's like you're turning it into a problem. It's not. That always is an indicator that you're like confused about something. I'm not sure how long it takes to clear up the confusion. Probably not long. But this is just a scale mixture representation. There's nothing Bayesian per se about this. Bayesians use these sort of representations. It might look and feel like some other problem to you. But in the context, it wasn't Bayesian. So it's just tricks that Bayesians apply all the time. So this right here is going to be a gamma, it's going to be alpha minus 1 e to the minus gamma theta. So I've gotten rid of a lot of normalizing constants that I don't need. We're going to be integrating over that. So again, it's not a function of gamma. Gamma's been integrated out, it's gone. There's no sums or anything like that. So this just is going to look like proportional. I'll get rid of the sigma squared, but I'm going to bring that around. Gamma, this is going to be that half power. It's the way that it comes in. I'm okay, I guess, with some people left that as a negative. Dividing by division is kind of hard for people. Me too. So, still would have thought if you knew properties of distributions, you would know that that has to be 1. So, or if you practice this. So, probably just an indicator of practice. E to the minus, I'll pull that gamma up. You'll notice I don't need the sigma squared in here. It's all up to proportionality anyway. It's not doing anything, but I can't use the gamma. So, and I think that's a common mistake. Easy to fix it. So this will be gamma, and I'll add everything together. Let's just take this one right here, and I'll just save myself a little bit of space and write down plus alpha minus 1. So some people did some funny things with that exponent right there. It's really probably just an algebra mistake. E to the minus gamma x minus mu sigma squared. There's a 2 in here, plus beta. Some people did some funny things with that 2 and didn't know what to do with it, and it would fly all over the place. Not a big error, no huge mathematical issues. Yeah. So, don't worry, you did really well. So, yeah, so proportional to that thing. And now I know what to do. This thing is a gamma kernel, with these being the parameters right here. And so this thing is going to be proportional to this thing raised to the negative that thing. That's what we learned a long time ago. And so a lot of people could get here. So I was kind of surprised that we couldn't finish it up. So especially since I said this was going to be there. That's the part that probably disturbs me the most. Like I thought I was giving you such a great hint. This is absolutely on the exam. So that thing right here. So a lot of people don't know what to do with beta right here. And they don't do all kinds of weird stuff. So, but this is the form. You could have your 2 beta in here and there wouldn't be the 2 in here if you factorized it in. But it's either going to be here or it's going to be there, depending on how you play around with it. But it doesn't just vanish. And so I'm going to factorize this beta out right here. I'm going to have another beta term down here when I do this. So I always do this in one step. And write down proportionality. Maybe that confuses you. So let's just leave it like that, and I'll show you what I'm actually doing. So this is going to be x minus mu squared over 2 sigma squared plus beta to the minus alpha plus 1/10. So this is just going to be x minus mu squared over 2 beta sigma squared plus 1 times beta to the minus 1/2 plus alpha. The same thing right there. I can take this beta, it's raised to a power, and factorize it out. So I can write this down. This beta to the minus 1/2 plus alpha right there. Gone. Proportionality. It's just a constant right there. That's what happens. That's what we're always doing. We're making that a 1 by factorizing it away. Now we've got the answer we're looking for. So I'm just going to write that out just a little bit differently. 2 alpha. Right there, same exact thing. I need this to be the degrees of freedom. And I need the degrees of freedom to show up here as well next to the scale factor. So this is also new. And so beta is equal to alpha is equal to nu over 2. Okay, so that's the answer. That's at least the analytic solution. That's what you needed to pick. The next two questions on the exam were meant to be easy. Again, a question about what do you know about distributions. So if there's going to be an expectation, if mu can be interpreted as an expectation, mu is just a number in all of this. So there's no constraint on mu. Mu could be any number, negative or positive. It's just the shift of all of this. So I want this centered at mu, and I want to interpret the mu as a mean, which is a special function. It has to have heavy enough tails so that that thing is a mean. And so what that means is that mu is greater than 1 for a mean to exist. So this was just a question about t-distributions. And so a lot of people get a little bit confused and think that has to be an integer. This can be 1.0000000000001. As long as it's bigger than 1, it does not need to be an integer. It just needs to be positive for it to be a t-distribution. And it controls the height of the t-phase. People get confused over, probably when they work with their standard error function, and they're thinking about the degrees of freedom in terms of n minus 1. But in general, it's an arbitrary parameter in a distribution. For the variance to exist, something similar happens. Nu is greater than 2 for variance to exist. So these are like things you either know or you don't walking into the exam. What becomes illuminating to me is when you don't know the answer and you just, you know, whoa, stuff. You know, lots of stuff. So it wasn't meant to be hard. And again, I don't mean to be punitive either, or to tease you guys too hard. So this is all meant to be helpful. As long as we can correct everything. In the beginning. Okay, so that's how you do this problem. Hopefully you can do it forever. I want you to just think about something though. When we're doing this, we go back up to what this problem is. I'm taking a normal distribution and I'm averaging over something. So I'm averaging over this gamma form. So gamma is just changing the scale parameter. So it's kind of moving and it's changing the scale parameter and it's kind of pulling it to the left and to the right a little bit. Small numbers, big numbers, and rescaling this whole problem. It's not reshifting everything so long as the way I do this is symmetric. So that there's symmetry to it all. I just want to point out that there's a symmetry to this if alpha and beta are the same numbers. So if gamma was a 1, I haven't changed everything. It's just the same. So if I put a point mass distribution on 1 and let this be a 1, gamma be a 1, it'd just be a normal distribution. I wouldn't have changed anything. I wouldn't have picked up tails by changing the scale parameter, fluttering the scale parameter. I want you to just realize that the expectation of gamma given alpha and beta, so no data in there, this is just a modeling technique that I use to lift the tails. This is alpha over beta, the way that I parameterize it. And so that thing is a 1 if alpha and beta are equal to each other. And I'm not biasing this thing in any particular direction. So in expectation, this is a 1. And so I haven't shifted the distribution. I haven't done anything weird to it. I've got something that I'm rescaling by, and I'm just kind of changing the tail behavior of it. So I want you to think about that a little bit when you're thinking about your distributions and what does it all mean. These numbers should be equal to each other, so on average, it's kind of centered in the same area. And if I changed those and they weren't equal to each other, I would have shifted this thing. And you can verify that for yourself. It wouldn't be centered at where you think it's centered. So think about that a little bit. Any like real pressing questions that you guys have? You just can't take it anymore, you need to know the answer? I think I've mostly covered. So there was this question, this is designed to catch you, to see if you know what Jeffreys priors are. So there is this question, you know, what's the Jeffreys prior? Oh, I'll do this one too, just while we're at it. And we can begin with hypothesis testing. Jeffreys. This question is designed to make sure after you go through the midterm you know what a Jeffreys prior is. You understand the whole point of it. Some of you got this. It was meant to be just this calculus quick problem. So, Jeffreys prior. It looks like this. So, information for lambda to the half power. So again, our problem is going to be fx given lambda. This was an exponential distribution. Some people take the lambda, flip that upside down. Same sort of thing. Lambda is positive. X's are positive. And all of that as well. And so exponential distribution. Quick question. The conjugate prior for this, most of you got this right. It is a gamma with arbitrary parameters, alpha and beta. Notice if I fix these parameters, let's say it like 0, 0. The posterior wouldn't be a gamma 0, 0. It would be a gamma something. So if I fix the parameters in there and I say it's always that and that's the general conjugate prior, the posterior won't be that form. So it'll be something else. And so again, just a little bit of an error. That's a -1. If you ended up saying it's a gamma 0, 0 or something. But there were a lot of connections in this problem. And so it's going to be some gamma. So again, we're thinking about those as arbitrary. Some other people came up with some other stuff like Poissons. I saw that only once. So, but I did see some other peculiar answers. Keep in mind that Poissons are distributions on counts. And lambda is a continuous variable. So that's your first sanity check is, what is lambda? And some people are interchanging the roles of x and lambda and all of this, in one short. Those were not very common issues. A lot of you were pretty close and could ultimately come up with something that was reasonable for the next question. The Jeffreys prior, right here, I work out my information. I think it's easier to work with the negative form of this and take two derivatives. Two of these, log, and I just plug this thing in. And then you just start chiseling away at this. So this is log lambda minus lambda x. Saw a couple issues with taking logarithms, so patch that up if you weren't able to see that this is that. Most of you could do that. And so this is going to be minus expectation. I'll take my first derivative. And so this is derivative of log lambda. It's going to be 1 over lambda minus x. I saw a couple times people had switched what they were taking the derivatives with respect to, and they fouled up their problem. So they take a derivative with respect to x here, and then lambda there, and then reverse it. Yes. So minor problem. If I saw that, I just made a note to you about it. Fixed it up for you. Not a huge issue, but it kind of starts compounding from the problem. So next derivative, super convenient. The x is going to be gone in a second. So this is going to be minus 1 over lambda squared. After I take that next derivative right here. Lucky us, there's no x in there. That's what this expectation is a function over. Lambda is a constant. So we don't have anything to do. Now, as promised, this thing is positive. And if it weren't, we'd know we had made a mistake. And so this is going to be 1 over lambda squared. So we go back here. If it were me, I'd forget to take the half power at the end of the day. So I'd probably do something like that. Don't think I saw that, to tell you the truth. That's just a me thing. So that's 1 over lambda. This is a beautiful thing. So this is a gamma 0, 0, so it falls into the conjugate class. So the Jeffreys priors are limits. of conjugate priors. So that's nice. Cool. We see that. So that's probably where some of the confusion arose. But this is a type of gamma, so there's a little bit of overlap with what we already knew. There's this question about scale invariance and shift invariance. This right here, if it were shift invariant, I should be able to shift around lambda and it doesn't make any difference. So I can look at a form of something, 1 over lambda 1 minus 1 over lambda 2, and if it were shift invariant, it wouldn't matter if I shifted this thing by lambda, and it would be the same distribution, but this is not equal to 1 over lambda 1 over lambda 2, so it's not shift invariant. It wasn't meant to be shift invariant. It is, however, scale invariant. And that scale invariant form always has this 1 over the scaling parameter. I'll just make a note. Note, lambda is a scale parameter. So lambda is a scale parameter, and scale invariant distributions, there's always that 1 over that parameter that shows up. It happens in location scale families. It's the Jacobian term. This is scale invariant right here. We've talked a little bit about it, maybe a lot. So it is scale invariant because it's a scale parameter, and the Jeffreys prior gives you that scale invariant form automatically, but it only does it for scale parameters. It did it for sigma squared, it would do it for sigma, it would do it for phi. The Jeffreys prior is 1 over phi, 1 over sigma squared, depending on how you parameterize your scale term. And that's how it comes out. So it is a scale parameter, and it gives you a scale invariant form automatically without you even knowing it. Some of you said, this was a very common answer, it's transform invariant, so it's scale and shift invariant. Those are different things. And it's not automatic. I wish you could have every type of invariance all at once. That'd be really nice. No matter what I do, I get the same answer. No matter what happens in the universe, everything stays the same. I don't know what kind of universe that is. Because anytime anybody changes something, something changes somewhere. So it's just a matter of what does stay constant. So what we mean by transform invariance is if I apply the Jeffreys prior form, I take those two derivatives over the log likelihood, then I take the expectation over that new parameterization. If I transform my original prior, I would get that exact same thing. So if we all agreed on using Jeffreys prior, regardless of our parameterization, we'd have the same answers. What that means is I can just take your Jeffreys prior and transform it directly. So Jeffreys or I could say D Jeffreys prior, no apostrophe, or, and I think I said log lambda. So every time I see the lambda, I replace it with something. What do I replace it with? I'm going to use this. I'm going to redefine the notation. This is what I always do. So lambda is going to be e to the psi. So every time I see lambda, I replace it with that thing right there. So all we have to do, and I made this note for those of you that didn't get this right, this is probably the most common problem. I don't consider it huge because I've seen this misunderstanding for 15 years, 20 years really. People in my graduate school also were confused about what this invariance was. So it means you can just do this. G inverse, I'll call this G inverse psi, times derivative G inverse psi. I don't mean I just transform this thing directly and every time I see the lambda I just plug in this thing. I have to do the Jacobian thing. So d psi. This right here is going to be e to the minus psi, derivative of, this is just plugging this thing in to what we found previously. Lambda is going to be 1 over lambda. So I take lambda, I plug this thing in, it's going to be e to the minus psi, derivative of e to the psi with respect to psi is e to the psi. This is 1. I just want to point out that scale parameters, when I take a logarithm over them, they turn them into shift parameters. So log scale parameters are shift parameters. So if you haven't made that connection already, here it is for you. So this is a flat parameter, flat prior on the log of this parameter, which turns it into a shift. Just keep in mind, if I wrote down my original distribution and I start thinking about logarithms, there's going to be a shift term that pops up. I'll have you work through that and just see that that's true. So just reparameterize this in terms of psi. You'll see that it's a shift parameter. It's kind of a nice thing. So if you worked with it in that formulation and you thought about it as a shift rather than a scale, on the log scale, place a flat prior. Connections you can make. I'll turn back the exams next time at the end of class so you're not spending the whole time figuring out what your errors are. And what if the point total is fair, I'll let you mull over it and then I'll let you come back and be on Friday. But I'll give you some things to think about on Wednesday. We'll go over it briefly. I think we got most of our work out of the way. Hypothesis testing. So it's something like this. This is your general setup. fx, given theta, you get to observe some data out of this. Maybe this is IID, maybe it's not IID, I don't really care. But if you'd like to think about IID cases, we can work with the IID forms and then work with non-IID stuff a little bit later. And you probably have some problem like this. So maybe f is a normal distribution and theta is maybe an unknown mean or something like that. Maybe the hand of the statistical gods gave you sigma. Or you're just maybe thinking about this parameter, something you want to estimate. And a question that's been coming up for about 100 years is this basic question. So questions. So these are hypotheses. Let me just ask real quickly, for those of you that have taken philosophy and logic and all of that, what makes a hypothesis a hypothesis? People say things all the time. It's just a hypothesis. It's a working hypothesis. And sometimes it is. It's falsifiable. Yeah, it's testable. So it's falsifiable. I think that's the correct way. We can't know anything is true, but we can maybe have proxies for the falseness of things. This goes into Popperian philosophy, whether or not you can falsify something. So we're testing it. Maybe it's true, maybe it's not. Yes, but we have a method for testing. We use the data to do it. And so it's not going to be like in math class where we reach an obvious contradiction. We're like in the realm of a contradiction, and that has huge implications. So what does a realm mean? How close is this to something? And I'll just tell you right now, and I'll keep saying this point, all the controversy is about how we define closeness, distances, things you're going to have to think about. If this were a Stat 101 conversation, this would be very hard, but since we're all graduate students, we can compare and see what we mean. And that's what we'll do for at least the next week. So these are maybe some hypotheses. So maybe you want to test, this is called the null hypothesis. Where does this term come? It's only your baseline hypothesis. It's just your hypothesis. So people like to say the null hypothesis. It's just lingo. It's your hypothesis that you're asking. Okay, so this is your question. Why do we call it the null hypothesis? Just to make it sound better, I guess. I don't know. It's kind of bothers me. Is theta equal to some value? So is theta some value that I pre-specify? Theta not. Okay, that's one question that people will ask. And there's some other questions that people ask sometimes. So this is called the sharp test. sometimes people will call this the two-sided test. That's really a bad name. And the reason why is it's alluding to a procedure for testing everything. It's not telling you about the question itself. It's saying, here's a procedure you should follow. And so sometimes people will call this the two-sided test. I don't care if you use that language. I don't like it. So how bad does it bother me? Just enough to leave it right there. So it's the sharp test or the point test. So I'm testing if theta is equal to theta naught at some point. Some people call it the simple test. So, AKA simple. You have different versus categories, what you're going to compare it to. So it could be compared to another point, that would be called the simple versus simple test, or you could compare it to a range of values, and sometimes people call that the simple versus composite test. This is where all the trouble exists. So we will go into this controversy. I'll tell you what controversy is all about in just a second again. There's other tests. So other tests. Maybe I'm asking, is theta greater than some value? So this is sometimes called the one-sided test. Again, it's alluding to a procedure, but you are testing on one side. So I kind of consider this reasonable. So one-sided test. This is not controversial. This one, a lot of people have come close to agreeing with each other. So not as much controversy. I'll say very little controversy. So, and we're going to talk about the reasons. These tests are wildly different from each other. So the way they behave, what people are answering with the different testing procedures, they can either be compatible in this. So what Neyman and Pearson's are doing is they're protecting error rates. Where Bayesians are giving you posterior belief statements on whether or not this is true. It turns out that in a lot of cases, those are very close to each other. However, in this paradigm, when you're testing this right here, controlling error rates and belief statements are wildly different. And so what you see is people arguing and they don't know what they're even arguing about or what they're even comparing. And so we want to understand this in this class. I'm just going to point out that this test right here, it's like, is this a real question? So if theta were continuous, I already know the answer. No, it's not. And so I don't think anybody is specifically thinking they're asking this question. They're asking, is it close? Close enough to not reject? Or maybe close enough to use? I call that an acceptance, but people argue over that. Let's not argue over that. You know, acceptance or failing to reject. Let's just call that all the same here. So I don't really care. I get the difference in offered perspective. You can't really know the truth, but you can fail to reject. Let's just leave it there. It's not any more interesting. We're all asking the question, are we close to this? But we're changing what we mean by close and what our prescriptions are for gauging closeness. I'm just going to point out that a Bayesian is calibrating a relative closeness on a relative distance scale, and the non-Bayesian is probably doing something on an absolute distance scale, or comparing it to standard errors or something like that. And so we need to talk about what that is. But a lot of times when we disagree, it's usually over the way we're making the comparison. And that's what we should be discussing. It's not, is this question valid? But if you want to ask it, did you come up with a notion of closeness that's reasonable? We need to talk about that a little bit. absolute distances or baseline distances in something like a standard error versus some well-calibrated, meaningful relative distance can all be wildly different. So everybody disagrees here. Some people say don't even ask the question anymore. But there's some caveats. Sometimes you have to ask this question. We'll be going into those details. So that's it for now, you guys. I'll pass back the exam. I'll show you what the scores are, what the distribution is. I'll give us some prescriptions. Until then, don't worry too much. And just start thinking about the exam and whether or not you understand the answer. I'll give you an opportunity to clarify. Thanks, you guys. That's it for now.